All right, so here's the problem. So we want to make a committee of 3 people out of 10 people in total. And we want to count how many different ways we can choose that committee of 3 people. So let's kind of write down what's going on here. Well, there's 10 people in total. Let's see if we can write down the state that these people can be in. So they're either, I'll use a check mark, I guess, to mean on the committee, or maybe a Y. I'm going to use letters just for ease, but there's nothing special about using letters. Like with that first example with bits and bytes, I used what the bits and bytes look like. So Y means on the committee, and N means not on the committee. So they are both states that these people can be in, and how many people are in each state. So how many people can be on the committee? Well, 3 people can be on the committee, which means 7 people are not on the committee. Let's make sure that I got every state that a person can be in. Well, I have 3 plus 7 is 10, so it looks good. It looks like I've accounted for everybody. And the way to think about this is, well, assign each person out of the 10 a position in the word. So if I write something like this as an example, this is just a little example, not the solution. But if I write something along the lines of N, N, Y, N, Y, N, 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 Y, N, this means that person 3, person 5, and person 9 are on the committee, and people 1, 2, 4, 6, 7, 8, and 10 are not on the committee. So assign everybody a place in the word, and this is how to write down who's on the committee. So, well, if we think about it, we want to count how many committees are there. The thing to realize is that each arrangement of this word gives a different committee. So, let's count how many arrangements there are. Well, there is 10 people, so 10 factorial on top. That's like pretending all of the 10 letters are different. And then we need to divide by the number of ways of arranging each of the repeating letters in the word. So there are 3 factorial ways of arranging the Y's and 7 factorial ways of arranging the N's. So that's 10 factorial over 3 factorial times 7 factorial. So this is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 factorial times 7 factorial. The 7 factorials cancel. And then, so this is 10 times 9 times 8 over 3 times 2 times 1. I see a factor of 3 in the 9, and I see a factor of 2 in the 8. So this is 10 times 3 times 4, which is 120 different committees. So I want to make note, this is kind of a special case that comes up quite a bit. So if you ever only have 2 states, 2 different states, so usually it's some sort of yes-no problem or something like that. But if there's ever just 2 states that each thing can be in, or two letters that you're arranging, two different letters, we call that a combination. And the way we write a combination, so combination is, you can think of it as a word arrangement with only two distinct letters. And let's say if there are n letters in total, and there is, let's say, r of one letter, well, there's obviously the rest of them, n minus r, of the other letter. And the notation that's common for combinations, because it comes up so much in mathematics, we have a special notation. We write n, and we say n choose r. Written like that with the n and r on top of each other, but it's not a fraction. There's no fraction line, just some brackets around it. And this means basically n factorial over r factorial times n minus r factorial. And so the way to think about it with the example up here is that, well, you have 10 people in total, and you're choosing 3 of them. So these are the one, hold on. So these are all of the people in total. These are the ones you're choosing, the Y's, and these are the ones you're not choosing, the N's. So we read it as N choose R. And so in the previous example, we would write 10 choose 3, which is 120, using that same calculation. So let's do one more example. Example 44.8. So in this example, you are making posters for the 100-meter dash at the Olympics. Listing the gold, silver, and bronze winners, and nothing else. How many different possible posters are there? If there are 8 runners. And so for this one, I'm going to think about it in 2 different ways. One's going to be the easy way. The other one's going to be in terms of arrangements of letters. Just because it's good to think in arrangement of letters, because you can do harder problems thinking in terms of arrangement of letters. But let's do it kind of the first way. So basically, you're only concerned about 3 positions. You care about the gold, then the silver, then the bronze. So, how many runners can win the gold medal? Well, 8 runners can win the gold medal. But once a runner wins the gold, they can't win the silver. So how many runners are left to win the silver? Well, 7 different runners could win the silver. And how many different runners could win the bronze? Well, the people who've won the gold and silver can't win the bronze now. So there's only 6 runners left that could possibly win the bronze. You multiply this out, you should get 336 different posters. That's not bad. I'm going to explain it again in terms of arrangement of letters, just to get used to that idea for harder problems. We'll do one more example after this, in fact. That'll be a little bit harder, where you can see it's more useful to think in terms of arrangement of letters. So, how many runners are there? There are 8 runners. And what are the different states these runners can be in? Well, they can be, let's use G for gold medal. And how many runners can win a gold medal? Of course, just 1. Well, what's another state the runner can be in? Well, they could get the silver. And only 1 runner can get the silver medal, and same with the bronze. Only 1 runner can win the bronze medal. And then what state are the other 5 runners in? Well, we'll use the letter X, I guess, for them. Did not medal. So they lost. And how many runners do not medal? 5 of them. And we check, did we cover all cases of the runners, of all possible states the runners can be in? Well, let's add up all the runners that are taken into account. Let's make sure we have them all. 1 gold plus 1 silver plus 1 bronze plus 5 did not medals. That's 8 runners. We've accounted for all the states. That's great. It looks like our problem is good to be solved. So let's scroll down, make a little bit of room. So again, we don't need to do this every time, but I'm just going to do it as an example just to make sure we understand what's going on. So let's say I had a word that looked like this: X, X, B, X, S, G, X, X. Well, this tells me that runner 6 won the gold medal, runner 5 won the silver medal, and runner 3 won the bronze medal, and the other 5 runners did not win a medal. So that's what this arrangement of the letters 1 G, 1 S, 1 B, and 5 X's tells me. And any arrangement of these 8 letters gives me a new order of finishing for the gold, silver, and bronze. So we just need to count the number of unique ways of arranging these. But we know how to do that. It's going to be 8 factorial over, well, the only repeat letter is the X, so we're going to divide by the number of ways of arranging our X's. 5 factorial, so this is 8 times 7 times 6 times 5 factorial over 5 factorial. So these cancel, and we're left with 8 times 7 times 6, which we just did, is 336. So again, it's the same idea, but it's a nice way of thinking it because you're thinking about what happens to all runners. This again is another special type of counting in math. This situation comes up a lot. So whenever you have a situation with only 1 repeat letter, we call that a permutation. Or you're arranging things and the order does matter how you pick them, is another way it can be said. But there's only 1 repeat letter when you think of it like this, and that repeat letter for us is X. And I will say usually in kind of word problems, it's usually a kind of, what do I want to call it? A do not care state. So usually in application, that repeat letter is the do not care state. Like, we don't care about the people who do not medal, so we put X's for them. Usually that repeat letter is some sort of state that we're not interested in, but we need to keep that into account. And again, Permutations are, they come up in math quite a bit. Not as often as combinations that I just talked about, but we call this a permutation, and we write it like this. So we write it as P, N, and then K, and this is the number of, let's say, non-repeat letters. And the formula for that, if you want to write it down, again, you don't really have to think in terms of formulas if you're thinking about arrangement of letters. If you're comfortable with this idea, the formulas just happen naturally, but it's n factorial over n minus k factorial. And so kind of you're dividing by, these are your kind of do not care letters. But this is the notation for a permutation here. And I will say, in future classes, you might see people go to formulas like that, and that's fine, but the way I like to think about it is all in terms of arrangement of letters, and if you're thinking like that, you don't need to remember formulas. And the final example we'll look at, 44.9 example. So it's going to be similar to the first one about the committees, except we'll make the committee a little more complex. So out of how many committees? Can you make? From 12 people with, so the committee is made up of the following thing. It's made up of 1 president, 2 vice presidents, 1 treasurer, and 3 members at large. So members at large are just committee members that don't really have a specified role, but they just help out whenever they can. But again, this isn't too bad as long as you're thinking in terms of arrangement of letters. So there are 12 people. What are the states these people can be in? Well, they can be president, and there's 1 president. They can be vice president. There's 2 of those. Use the letter V for that. Treasurer, let's use the letter T for treasurer. There's 1 treasurer. And there's 3 members at large. Let's use M for members at large. But that's not all of the people. We've only accounted for 1 plus 2 is 3, plus 1 is 4, plus 3 is 7 people. There's 5 people left. They're not on the committee. So let's use the letter X to denote those guys. So not on committee. And remember, any arrangement of 1P, 2 V's, 1 T, 3 M's, and, well, there's 5 people left, so 5 X's, any arrangement of that would give you a new committee. Wherever the P is, that would tell you, say the P was in position 9, that would tell you that person 9 is the president. If the V's were in spots 2 and 11, then people 2 and 11 are vice president, etc. So let's count this. So 12 factorial, the number of people we have, and now we just need to divide by the number of ways of arranging each of the repeat letters in our word. So 2 factorial, 3 factorial, 5 factorial. Let's simplify this. 12 times 11 times 10 times 9 times 8 times 7 times 6 times, I'm going to cancel out that 5 factorial, so I'll stop there, over, I'll write it like this, 2 times 1, that's 2 factorial, times 3 times 2 times 1, that's 3 factorial, times 5 factorial. I know that the 5 factorials are going to cancel. It's always a good idea to kind of cancel out the largest factorial in the denominator. And then let's hunt for factors in the denominator that are also in the numerator and cancel them out. So I see, oh look, a 6 has a 3 and a 2. And let me use a different color just to make sure you know what's canceling with what. So the 3 and the 2 cancel with the 6. And I'm left with another 2. Let's take it out of, I don't know, this 12 to make it a 6. So now I have this here, 6 times 11 times 10 times 9 times 8 times 7. Whatever that number is, that is the number of committee members. Or sorry, the number of different committees I can make out of these 12 people. And if you multiply those together, you get 332,640, which is quite a lot if you think about it. It's a bad idea, especially with counting problems that have where you're arranging more than 4 or 5 things. It's a very, very bad idea to try and list every possible scenario. If you do that, you'll be there forever. I mean, for this example, you would have to list over 300,000 different scenarios, so it's best to count using some systematic method like we've been doing. Usually listing, unless it's really small, listing to count is an arduous and untenable